Good morning, students. Well, at least if the forecast is correct, we're going to enjoy some nice warm weather, and then towards the end of the week, it's going to get cold, or at least it's supposed to get cold. So I'm interested to see how that fares. A lot of times we think, well, maybe we might get some snow or something, and occasionally we do, but that's something probably that will not happen. But if it does, it's kind of a cheerful thing. It's after Christmas, or the holidays, but it's still kind of nifty. So if you enjoy the cooler weather, we'll get a little bit of that. Today, what I want to do is start talking about more general aspects of polynomials. The last class, we actually investigated the quadratic polynomial, which again, there's nothing that we don't know about it. We basically looked at all the aspects of the quadratic polynomial or the quadratic function, and we can optimize it. We understand its graph, we understand its symmetry, we understand ways to compute vertices using x-intercepts like we did with the word problems. So it's really a function or polynomial that's our friend. And what we want to do today is look at a more general polynomial and just basically look, for instance, if there's certain characteristics about the polynomial that we can exploit to maybe understand it, and maybe just investigate some of those ideas, and then say a little bit about what it means to take these objects and divide them. We're pretty good with polynomials when we add them. The objects are, we can add them, we can subtract them. We have the distributive law. So we do have what we call a linear algebra with polynomials. We can multiply them, and that's fine. But the division process is probably not something that you know as well, but we want to try to integrate that into one of our operations, and then discuss a couple of results that'll be very useful to us when we look at finding zeros of polynomials in general. The idea of computing zeros of a polynomial is actually quite difficult. In general, it requires some analytical techniques that you will learn in calculus and numerical analysis. But you can always, with arithmetic computations, zero in on a polynomial. But what we'll try to do in this class is focus on the zeros that we can compute by standard techniques. Now, for Thursday, you have your first test coming up. I just wanted to say a couple of things about this. For Thursday, we actually have a college community day, and so that's a free day for you. Even though the test will run from Thursday to Friday, you can take Thursday off if you want, and then just test on Friday. I'm giving you that 2-day window. That we have a college community day, which basically brings the college faculty and staff together to do other things. And what I plan to do on Thursday is I will present some review problems in the lecture format. Now, as with this lecture, it's being recorded, and it will of course be posted, the link posted on Blackboard. So what I'll do on Thursday morning during our regular class time is present some review problems, like go through a practice test like you have on Blackboard. You've got plenty of practice tests in the format that will be covered for your first test. And so I want to go through some of those problems. Now, again, it's not required that you attend because you do have a flexibility day. But I will post that actual link so you can utilize that as some review. Some of you may not need the review. You may be very prepared, and that's fine. But I do think it's good just to have a day just to kind of summarize everything and give you an opportunity to review some other problems. Again, use it as you like. You are in control, and so you decide how you want to utilize that. But again, let me just emphasize, you will not have to attend, but if you do attend, it'll be like a regular lecture, and I'll say good morning and whoever's here kind of thing. So I always appreciate the good morning. You all are just wonderful to be kind to each other and to your professor. So very good. Okay, so what we want to do now is go ahead and talk about some polynomials. So let's go to the document cam, the IPEVO. And so when we think about a polynomial, we think about an object that's a finite sum. So a lot of this discussion will be very straightforward and probably things you've talked about, but in general, what we want to do is to exploit whatever characteristics the polynomial has, maybe to sketch a reasonable graph without calculus, and maybe just to understand a function a little bit more so than maybe we would ordinarily. So polynomial functions and their graphs. Not a computer generated graph, just a reasonable graph. Sometimes I'll call it a cheat graph. We use the basic characteristics of the polynomial to get a reasonable graph, not Rembrandt, but just reasonable. So, oh, I've got my cuff here that's not buttoned. I don't know it's weird. This shirt, when I have it cleaned, they put so much starch in it that I think the cuff is already buttoned and it's not. So let me do this. Otherwise I'm gonna lose my mind as I try to lecture. Sorry about this. These buttons are rubberized, so of course they don't work very well with my long fingers. There we go. Let's see, did I get it? Yeah, sorry about that. So let's look at real polynomials. So what we'll have is P of X for now, and we'll write this in descending order, A sub n, X to the n. So you can think of a polynomial as having this general form, and often, you know, we think, well, if we factor a polynomial, it doesn't look like this, but if it's unfactored, it has this nice descending form if we choose to have the largest power of X first. So the next term, A sub n minus 1, X to the n minus 1. And then we'll just descend to the quadratic part. For instance, here, if the polynomial started here, this would be a quadratic polynomial. And then, of course, the first degree term, and then a constant term. So in this particular case, what we're seeing and what we're going to use in this case, usually we'll just have our A sub I to be real numbers. It's certainly possible to have a polynomial with imaginary coefficients, and that's fine. We're going to have imaginary zeros, but we're probably not going to focus on so much the imaginary coefficients, but that's certainly possible, and I will mention that. But for now, we'll just stick with the reals. Let me grab there we go, little focus there. And also note this, n, in this case, is a natural number. So we'll say powers of the variable, and it can be any variable. We have X here. Powers of the variable X are non-negative integers. So polynomials are pretty strange. Fairly flexible. Here, let me write that so you can see it. It's good to be able to read it. Integers. And so we don't have polynomials that have a 1/2 power in them. So we look at the quadratic polynomial, that's an excellent example, squared, and then possibly a first degree term and possibly a constant term. Now, when we write a polynomial, this is what we call the leading term. It's also the dominant term. So the leading term is a sub n x to the n. Basically, the leading term includes the largest power of x. And in this case, and this is very important, a sub n is always assumed to be non-zero. So when we write a polynomial, the leading term, just like with the quadratic function, we have to have the squared term, but the other terms could zero out. So the leading term is a sub n times x to the n, and of course that leading coefficient is assumed to be non-zero. We define the degree of p of x to be, and we write it this way, we just say DEG, and usually we're just kind of lazy, we'll just do p and not the x dependence, equals n. So basically what we have here, we take the leading term, and that includes the largest power of x. Like with the quadratic polynomial, the degree is clearly 2. For a cubic polynomial, the degree is 3. So whatever n is, which we get from the leading term, that defines the degree. And also, the leading term is sometimes called the dominant term. We call a sub n x to the n the dominant term. So these are all terms that you may or may not have heard before, but they're important, at least in the sense that if I say, okay, here's a 4th degree polynomial, first thing you think about that, okay, I've got integer powers of x and I've got a 4th degree term. I don't know what else I have, but that's what I was told I was going to get. So I know I have the leading term. What you have beyond that, it could be anything. So we don't want to refer to a polynomial. I mean, of course, we can think of the zero polynomial, and that indeed is a polynomial. All the coefficients would just be 0, and so that's kind of odd. But 0 is a polynomial. 3 is a polynomial. It's a constant polynomial, and so and then that's when we think, oh, okay, so we're going to define x to the 0, as long as x is not 0, to be defined as 1. So this is a definition. What the 3 bars means exactly equal to. So we're going to say this is a definition. So we don't, we've used this before, but we don't want to get caught and say, well, is 3 a polynomial? Absolutely. We can just say p of x equals 3, and then we could just, say, okay, that's just the 0 term, the 0 power, because this is the same as just 3 using this definition. So the polynomials, again, we just want to delve a little deeper into what they're all about. Now, of course, as you do more mathematics, the abstraction increases, and you look at linear algebras, and you look at unique factorization domains and things of that nature, which this provides the groundwork for. So those of you that go on to take more math, you'll see more of these ideas and think, wow, we got that start in pre-cal, and now we're going to get even more abstract and see where that takes us. Now, what can we do with this? Well, I want to focus on the dominant term and then zeros. Now, when it comes to figuring out n behavior, we're going to look at this and say, okay, this is a very user-friendly function. We have no radicals. There are no variable denominators. And so any real number would work when we think about the domain. So unless we restrict it, the domain of the polynomial here, the real polynomial, is all real numbers. So the domain of P is all real numbers. Now, of course, if we were doing one of those applications from our last lecture where X was the number of units produced or manufactured, we may want to limit the values of X to be non-negative integers. But again, when you draw it, you draw the graph that includes all the numbers between the integers just so you can get a picture of it. Otherwise you just have discrete points plotted that would be in the shape of a quadratic or a parabola. So when we think about sketching a polynomial, ladies and gentlemen, we're going to always assume that the domain is all reals unless the problem says restrict to a certain set. And then if that's the case, we can say, how do we get that cheap sketch? Like Professor Ron, we could figure out the zeros, and that would be a big help, maybe with a sign test and local behavior. But how are we going to know what happens as X gets very large or very, very small? And this is where we can use the dominant term. So we'll just say in behavior. When you think about in behavior, it's like, okay, as X gets really large or really small, how can we just get a relative picture of the actual graph? So in the first case, we'll just say number one, we'll just say X greater than 0. This is going to correspond to the case where X becomes arbitrarily large. So you just think of a number that's positive, 500 or something, or anything positive, it won't matter. And so we'll look at it this way. We'll say A sub n, we look at the dominant term right here. If this term, when you just substitute a positive number, is actually positive, then this implies that we'll just use some limit notation. The values of P become arbitrarily large. And we'll just say infinity. What this is saying is that the smaller powers of X do not have as much control over the size of the function as X becomes arbitrarily large. The dominant term, that's what we call it, it dominates. And so all of the other lower degree terms kind of pale in comparison. So all we have to do is just figure out the sign of the leading term. And when X is positive, if this is positive, then we go to infinity. Now, of course, if we go in the other direction, if the sign is less than 0, then this implies that as X approaches infinity, a P of X, we get arbitrarily small, negative infinity. So there's nothing difficult about this. In behavior is nothing. I mean, you're thinking, well, it would really be nice if the problem is written this way. If not, you may have to kind of pick out the X values and multiply them, thinking of the distributive law to figure out what the leading term is. And so factor form may be a little bit more difficult, but it's still easy to pick out the values of X and just drag along with them the actual signs that come with them. So again, if the leading term is positive, when X is positive, the end behavior is infinite, and we think the graph just rises. If X is positive and the leading term is negative, then as the values of X gets larger and larger, the output becomes more and more negative. And so an end behavior would be that the graph would start to fall as X gets arbitrarily large. Now you're thinking, what happens in the other direction? 2, we're going to assume that X is less than 0. So when X is positive, we think about the case of X getting arbitrarily large. And now we want to think of the case when X just gets arbitrarily small, as negative as you like. And so now we do the same thing. We look at the leading term. So you take your positive x, excuse me, your negative x, and you check the sign of the leading term. If the leading term is positive, then this implies that the limit as x approaches negative infinity of p of x will be positive. That is positive infinity. So the positive here and the positive, see, positive, positive, negative, negative. Again, it doesn't, just because x is approaching negative infinity doesn't mean that the values are becoming negatively infinite. It just depends on the dominant term. There could be a negative sign in the dominant term that flips the sign. So again, there's no guesswork in this at all. You just simply look at the dominant term and say, okay, what are the signs? And then of course we think about, even powers absorbing negatives, odd powers retaining the negatives, just like we did with the even and odd function. So we get to use that parity that we've done before. Now, of course, if the leading term is less than 0, when we substitute an x less than 0, then this implies that as x approaches negative infinity, becomes arbitrarily small, then the output does likewise. So the idea here is I wanted to give you just a recipe that you can always apply. You can put this on a note card, just think, what's that dominant term tell me? What's the sign of the dominant term? And then you're done. Just remember, this is where we're basically using calculus, because what is happening, like I said before, is that the lower powers do not have impact. They start to fade their impact as x becomes arbitrarily large or arbitrarily small. And the dominant term, again, presides, dominates, so to speak. And again, when we draw our reasonable graph, it doesn't go on at infinitum. We just say, okay, the graph is going out to infinity, and we just, do a little curve that shows that. So we keep it really simple, but, our graphs are just reasonable depictions of what's going on. Nothing, precise to the point that we think of a computer generated graph. What we want to do is get a reasonable picture. And then that reasonable picture can help you to make certain deductions. Okay? Now, one thing that I want to talk about is the local behavior. Then we'll just do a couple of examples. Now, zeros of p of x will simplify the sketch of p of x. So for instance, if it's possible, at least for us to figure out some zeros, we can do a sign test. And we're thinking, that sign test would be really nice. Now, how do we do this without having to do so much work? I mean, we think about it. If we're doing transformations, we take a few simple points, we move them, and then we sketch the polynomial or the actual function based on the shape of the parent. And so we minimize the amount of work. So how can we keep that same routine with polynomials without feeling that we have to check 10 or 20 points, which again would pretty much be useless? So we can use, like the end behavior, maybe the polynomial grows in both directions. Maybe it does something like this. We'll check that. That's pretty simple to do. Now, how do the zeros help us? So here's what we'll have. We'll say given. In this case, suppose C is, and this is where we're going to use the division process, but it'll be intuitive, and then we'll state it formally. Suppose C is a 0 of P of X. That is when we, like, we found x-intercepts for the quadratic functions. We have a 0. That means if we replace x with c, the output is 0. So that says P of C equals 0. Now, of course, we have to this is where Dr. Stewart was probably thinking I should have done it backwards or whatever, but this will be good. And then when we get to the factor theorem, it'll make even more sense. So this implies, or equivalently, that basically we've got to have, I'm giving you the factor theorem first. And so when I go over it, you'll be like, well, he sounds like a broken record. This means that we're going to have some factor of x minus c hanging out to some power, say m, times some other polynomial. We'll just say where q of x is a polynomial. In this case, we'll just say real polynomial. We'll always assume that. And you could do like the R bracket. Remember, we have that notation for the ring of polynomials with real coefficients, if you want to think about it that way. So we're thinking, okay, so that makes sense. That makes sense when we do the zero product. You say 5 is a 0. Well, if you back up, you have to say, oh, okay, well, x minus 5 was a factor because it's basically the zero product theorem. So again, the factor theorem's tied into that. So we think of m as being what we call the multiplicity. So here we go. So m, in this case, case 1, say m is even. Say we factor this and we have this occurring to an even power like 2. Then this implies graph of P of X touches the x-axis at C. Touches. The even, this is what we call local behavior. The graph will not cross, it will only touch and then move away. So we're thinking, if we have the C here, I'll just do maybe two cases of this. We could have something going on like this where we touch, or maybe we have something like this, touch. The even multiplicity will dictate the local behavior, so to speak. And this is just a sign test. It's not hard to prove. Because of the even multiplicity, the graph will not cross. It will touch. So you have something like this or something like this. So when you factor and you think, well, if I get a 2 here or a 4, that'd be kind of an interesting situation with a root or 0 of multiplicity 4. You're going to have the touching. So the idea is that in a lot of the examples, you may see some squares. So you'll see multiplicities of 2. Again, an even number, which would dictate these types of local behavior. Now, the other one, you're thinking, oh, okay, what about the multiplicity m is odd? Well, this is exactly what you think. This implies the graph of P of X crosses the x-axis at C. So when you think of this, you're really thinking of the sign test. This is the BV technique, so to speak. So for instance, we might have something like this. Or maybe we have something like this. So again, this in conjunction with the sign test and the end behavior you're thinking, well, I've got these zeros, so I could think it's got a cross here. So for instance, when you do your sign test, you're thinking, oh, okay, well, in this case, I'm above. Well, it's even multiplicity, so I have to stay above. And so you can kind of do a little graph. It's not the graph of the function, but like I sometimes will just draw what appears to be a graph saying, okay, we know that the values here must be positive because of the multiplicity being 1. We've got a cross, so we're going to go from positive to negative and then back to positive. So this little local behavior in conjunction with the sign test and in behavior can give you an enormous amount. That's why I say simplifies the sketch. And then maybe you're thinking, well, you can do the y-intercept, just set all the x's equal to 0. Now, the only thing that this doesn't do is give you the calculus part, the maxima and the minima, the relative maxima and relative minima, the peaks and the valleys. That requires calculus. And so when you make your sketch, you'll think, oh, well, I have to rise, then I have to come back down, but we're not going to worry about how high you have to rise or how low you have to go. That's not the important part. That's going to be something you do in calculus. What we want to know is that the shape of the graph will be like this. And then when you get to calculus, you will refine it. You'll get the shape operator of concavity. You'll have the first derivative to figure out the extrema, the extreme values. So what we're going to do in pre-cal is do as much as we can to get a reasonable graph. And then in calculus, you're going to dress it up and you're going to finish the story. Okay. So what we want to do, let's just do a simple example. And then you're going to think, wow, Professor Ron, maybe you should put this on the test. This is easy. And it is. So let's just say I'll give you something that's a flash from the past. So we'll have x minus 1. Of course, I have to do this since I beat it in your heads last lecture. So here's an example. And we'll just say sketch p of x. And what that means is just provide a reasonable sketch. And you're thinking, well, that's a quadratic function. We can do even one better. With the quadratic functions, you get the best sketch. Okay, we didn't prove the concavity and the increasing decreasing, but we know the vertex is where all the action occurs. So if we look at this and say, all right, let me get this oriented so I've got more room to work here. Here we're thinking this is not in the standard form, but notice if you multiplied it out, the leading term, we can just say leading term. You can just look at it. The leading term is x squared. So we know what's going to happen on either end. Is x is positive or x is negative, it's still going to be plus. So the end behavior will go off to infinity. We're like, that's easy. So if you look at this and say, okay, well, we can do the little sign test, but let's just go ahead and use the construct that I gave you last time. We see what the zeros are, or the BBs. The zeros are 1 and -2. And while we're at it, we might as well just go ahead and get the vertex. So we can do just like we did with the word problems, the midpoint without having to multiply it out will be 1 minus 2 divided by 2. So that's -1/2. So that's the H, just like we did with the word problems. Remember, the segment created by the intercepts is bisected by the axis of symmetry. So that gives you the x coordinate of the vertex. And then now, of course, we can just get the K. So that'll be P of -1/2. Kind of like we're doing the word problems and we go back to the nice factored form because it's easier to work with. And so we have -1/2 minus 1, and then -1/2 plus 2. Well, of course, the first one, that'll just give us a -3/2. And then, of course, 1/2 from 2 is 3/2. So we get a -9/2. So this is a little extra that we wouldn't have for like the cubic polynomial or the 4th degree polynomial because we don't have that theory. And so now you're thinking we've got a vertex, we've got the zeros, and then if you want to think about the little sign test, you've got -2 and you've got 1. Well, with the end behavior, we can just say the limit of p as x approaches infinity will just be infinite, because again, we just take a positive number, and of course x squared is positive, so we get that. And then the limit as x approaches negative infinity of p of x. Again, substituting a value less than 0, the negative is absorbed, so we still get infinity. So we know on either end, we're doing something like that. But these have odd multiplicity. So we got to cross. That's what I've been doing before. You've got to cross. So what we see here is like, okay, if we didn't have this beautiful quadratic function, this would be extremely helpful. But we know that we have to cross here because of the what? The multiplicity of the zeros. And so we get that basically for free. And so above here and then below here. And so when we do our sketch, we can just use that idea. But of course now, you know, we know our picture is going to look a lot better because the quadratic functions we understand completely. So I'll just space this out so we can write it out. So we'll have what? Zeros 1 and -2. So we'll have a 1 and a -2. So go ahead and dot that. So we got 1, -2. And then of course we have a negative, and of course I'll have to do my scale a little bit different here. When we look at this, this will be a -4 and 1/2. So I'll do my scale a little bit smaller here. So 1, 2, 3, 4, 5. So about right there. And then the -1/2. So the vertex, I'll go ahead and write it out formally, is -1/2, -9/2. So we're about right here. So the -1/2, so that puts us about right here for the vertex. So we know this for free. We got this for free. So it's fine. So we have a vertex -1/2, -9/2. And so now notice the constant term is -2, so we're going to cross through here. Let's see here. So now, let's see. Oh, you know what? I thought that looked a little bit small. That's a 4. My goodness. That looked a little bit large. So yeah. So this gives us what? A -2 and 1/4. Yeah, the scale was a little bit bad. I said, oh, that looks a little bit low. So let's move this up to where it should be. So here we're going to get a -2 and 1/4. So we've got a 1, a 2. So we're about right here. Yeah, that looks a little bit better. So we have vertex. And let's see, we've got -1/2. So again, this is extra that we get. And I'll go ahead and make the change here. 4. And so we'll cross through, and we can just say here, notice P of 0 equals -2. So we can go ahead and sketch this. So if you like, since this is kind of review from last time, we can go ahead and put in the axis of symmetry, since we know that from our quadratic function. So this is x equals -1/2. Now, of course, I did this just to show you that our technique for the general case is completely consistent with what we've already done. So again, when you look at this, you're thinking, wow, that's a nice graph, Professor Ron. That's a really nice graph. Well, we get a better graph with the quadratic because we understand it. And we know that that is an absolute minimum. -9 is an absolute minimum, not a relative minimum, not a peak or a valley. It's absolute. So of course, with the quadratic function, we can get a beautiful picture. But the only thing that the calculus will do, like when we look at this, we can see that the graph is rising here, and we can see that it's falling or decreasing here because we understand it. But when you get to calculus, you'll be able to prove that the concavity here is upward, and you'll be able to prove decreasing then increasing. So for instance here, just know that with the quadratic function, all of this is valid, but we get a much better output here. So I wanted to throw this one in just as a good example of how we can do the same assessment for a less simple polynomial. Okay, so let's now do a less simple one. So again, use this as kind of a review of what we've already been doing. Now, the other example I wanted to talk about, let's see here, let's do an example that kind of throws everything together. We'll use our nice technique, but I'll throw in a square. This was from your book. So here, what the author does is he gives you a polynomial that's actually squared. So we have 1/8, excuse me, and we have 2x to the 4th plus, of course, this will factor by grouping. We don't have to use the stronger theorems, 16x minus 24. And then he squares it. Now, here's the thing, and this is why this is a good example. We get to use all of our bells and whistles. But I thought it's a good example that basically shows us how we can use all of the local behavior, in behavior, and the zeros. Note, this is just a polynomial times a polynomial. So the actual degree is going to be 8, but we square everything. So all of the multiplicities will have to be even, okay? So again, this, if you look at this function, it will either be 0 or positive. Again, there's no, the coefficient here is a positive number. So we can see just by looking at this and not even recognizing that it's a polynomial, that P of X is always non-negative because it's a positive number times something squared. And so our graph will never fall below the x-axis. So this is an excellent example. And again, we'll use the same techniques. Now, while we're staring at this, let's just kind of look at this and say, okay, well, let's get the leading term. This is, you don't have to multiply all this out, just look at what's obvious. When we square this, this will have the largest power of x. So the leading term will be 1/8. And then, of course, we'll have 2x to the 4th quantity squared. And then when you look at that, okay, well, we can work with that. So this will be 1/8. Let me write that so you can see it. So we have 1/8 times 4x to the 8th. And of course, the 4 will absorb into the 8 and give us 1/2 x to the 8th. That's our leading term right there. So again, that tells you just what we said before. Even though we don't really need it, we see that when with this positive or this even power here, then the end behavior will always be off to infinity. So this implies that the limit as x approaches infinity of P of X will be infinity. Now, of course, if that were a negative, we had a negative here, then both end behaviors would be negative infinity. So this could flip everything if there were a negative here. So again, the sign of the leading term is very important, but we already knew this would be the case, but we want to verify this. And then of course, the limit as x approaches negative infinity of p of x will also be infinity. Again, when you check x positive, this sign is positive. When you check x less than 0, this sign is still positive. So the end behavior in both cases diverges to infinity. Okay? And we expected that. Now, what we can do is say, okay, well, in all of these cases with the zeros, the graph will just touch. It's going to have to touch and then move back away and not cross. So let's verify that and then get what we call a cheap sketch. Now, one more thing I want to tell you about. Remember on the last one, it was easy to find the constant term. Notice here's a constant here, and we're going to square it and multiply by 1/8. So let's go ahead and get the constant term just so we can, know it. You can always plot the y-intercept, or at least make a note of it. So in this case, this is p of 0. So this is going to be 1/8. Of course, when we substitute 0, these are annihilated, and we're left with a negative 24. So we get 1/8. And then, of course, the two negatives absorb. So this will just be 3 times 8 times 3 times 8. When I teach calculus 2, they have so much arithmetic in their problems that I show them how to factor things so that they just don't go absolutely crazy. Otherwise, they look at it and say the arithmetic's harder than the calculus. So now, if we rewrite the 24 as 3 times 8 and 2 copies of it, we see that this 8 and this 8 will absorb, and that will give us a 3 times a 3, which is a 9, times an 8, which is a 72. So we're seeing that the y-intercept in this case is 72. Now we're thinking, you're not going to put 72 tick marks on the y-axis, obviously. You'll just kind of note it and just say, okay, this is what we're doing. Again, you don't have to be that particular. You can space out the zeros so you can have an easier picture of it. But then, of course, we just kind of look at the outputs as being scaled in the sense that, well, here's the y-intercept, and the graph can possibly get, more positive, and then we can dip back down if we have to catch another zero. So the idea here is that just the basics are all we want here. We don't want anything complicated. Now, when we look at this part, we're thinking, okay, well, Professor Ron, we've got the end behavior, we've got the 72, the y-intercept. What about the zeros? Well, let's go ahead and factor by grouping, and this is easy. Again, I'll always give you a problem that you can factor or use the quadratic formula. Now notice here, you can see some nice factoring if we factor by grouping here. So in the first case, we're going to say, okay, well, in both of these cases, we have an x cubed term. So we can factor that, x cubed, and that'll leave a 2x plus a 3. Now, of course, here, if we look at these two terms, we have a negative 8 in both terms. So we're going to say plus negative 8. And of course, that'll leave behind the 2x and then the plus 3. And this is all squared. So when we look at this problem, let me get a focus. When we look at this problem, we're thinking, okay, well, this is kind of like doing Professor Ron's AC limit, but we didn't have the AC part. So now we have 1/8, and then we have x cubed minus 8 times 2x plus 3. So we get to use our difference of, a difference of cubes. Now we know that this is going to be x minus 2, and then we'll get the x squared plus the 2x plus the 4. So we have that a cubed minus b cubed. is equal to A minus B. Let me write this so you can see it. A minus B, A squared plus AB plus B squared. So that's a formula from the very first day. But we know that this part actually gives us imaginary zeros, so we don't worry about it, at least for this graphing problem. So we get 1/8. So we have x minus 2. So in this case, the A is x and the B is 2. And we get x squared plus 2x and then plus 2 squared, or 4. And then, of course, I won't go ahead and factor that more. We know that the 2 would come out, as the coefficient there, but I'll just leave it there for now. Makes it a little bit easier to see the multiplicities. And then again, you can revive it, so to speak. Now notice all of these get squared. So we get 1/8 x minus 2 squared, and then x squared plus 2x plus 4 squared, and then 2x plus 3 squared. Now, the reason I wanted to do it like this is because I wanted to write it in a way that supported the non-negativity, so to speak. This is a non-negative function. So now you can see that even though this particular term, these roots are imaginary here, so we don't worry about them, at least not for now. We'll review the imaginary zeros soon after the first test and review that aspect. But now, of course, we have real zeros here and real zeros here. And of course, this would just be a -3/2 if you use the zero product. But again, I didn't go ahead and factor the 2 to move everything around. I just wanted to kind of get this at this point so you could see it. So now we can say equivalently, the zeros will be 2, and we'll say multiplicity 2. And then, of course, here we get a -3/2 by zero product of multiplicity 2. So again, this now supports the fact that the function's non-negative. So you can look at this problem and say this kind of gives us a little bit of everything. We check the zeros, we check their multiplicities. So in both of these cases, the graph will touch the x-axis at these zeros. We know the end behavior. We've got that y-intercept, not that it's any great deal. We could still get a reasonable graph, but we know it's all going to exist above the x-axis or on the x-axis. So now we've kind of beaten it to death. And so let's go ahead and do this. Let's go ahead and get a reasonable sketch. So I guess I don't have to worry about having many negatives. So I'll just go ahead and put the x-axis here. And we'll just scale the y-axis just to put in the 72 and not worry about it. We'll spread this out just so you can see it. So we'll have a 2, and we'll have a -3/2. So again, this is just a reasonable sketch. Don't worry that it's not Rembrandt. That's not what we're looking for. Even in calculus, we can refine the sketch, but this is just a reasonable rendering of the graph. And that's where we use our analytic techniques. And in pre-cal, we can do quite a bit without the use of calculus. And now we can just say, we'll say this scale is really, really small. So we'll just say, here's a 50 and here's a 100. And so our 72, say about right here. Okay, so we'll just, use a scale that we can tolerate. So the scale much smaller. So now we're thinking, okay, we've got the end behavior. We have to touch Then we have to pick up, if you want, you can go ahead and mark that in as a 72. We have to pick up this, but then we've got to head back down, touch, and then move back out. So let's draw it. Again, you know, reasonable graph. We'll pick up this. And okay, we're going to think, well, we're going to have a peak. We don't really know where it is without the calculus. So we can come up and then back down, nice and smooth, and then back up like that. Now, one thing I want to tell you about that's very important with these functions. Polynomials, see how smooth this is? The quadratic function is nice and smooth. No points, no corners, no, and it's continuous, no breaks. So when we draw this, we want to make sure that it's nice and smooth. You know, we come in nice and smooth and then move back up. We don't come in at a point. There are no creases in the curve. It's like as your little ant moving along the curve. It's a nice curvy road, but it's very user friendly. So we say that the polynomial function is not only continuous, but differentiable on its domain. And that'll be something that you'll do more with in calculus. But look at this. We're thinking, okay, well, these are minimum values right here. 0 is a minimum of this function. And we all know just from this deduction, 0 is an absolute minimum. We got that without calculus. The absolute minimum, the minimum of this function is 0. We know that. We don't need calculus for it. However, we are not really sure what the value here is of this relative maximum. That is, we know we have to move through 72, but then we've got to come back down to pick up the 0. So we will have to use calculus to figure out that, and that would be a difficult problem in the sense that we will have to analyze this. And then we've got to analyze a cubic polynomial that may require us to use an approximation method called Newton's method. So the idea in general, when it comes to finding zeros of polynomials, you never get away from it. When you get to calculus, it's worse. So everybody thinks when you get to calculus, it's just fun and party time and everything's easy. No, it's worse. That's why I'm pushing so much of this. That's why I'm so meticulous about what I do. And I want things to be clear and clean. If I write something down and I say 2 times 2 is 2 instead of 4, then I've got to work back through my work. And here's the thing. If you have an error, then the error shows itself. And then you've got, oh, let me trace back through my work. Oh, there's something I need to correct. So mathematics is self-correcting if you allow it to self-correct. That's why when you do your test, you write down your work. You know, you got the problem, you on a separate sheet of paper, you're done, you scan everything and you submit that to me. Because again, this is your game plan here. This is what tells me that you understand the flow of the logic. And of course, it doesn't have to be perfect, but it has to support your answer. So now, again, the idea here is that you're thinking, well, Professor Ron, this is just basic stuff. And truly it is. But here's what's nice about all of this. This is always true. So if you're doing some fancy calculus problem and you're thinking, I need to get done with this. I've got 5 minutes left on this test. Oh, this is always positive. Well, it's kind of look like this. And maybe you don't get to this part of it, but you've done a large part of it. You see that maybe you're doing a problem and all you really need to do is figure out the minimum. And you're thinking, well, this is non-negative and it does have a 0. Well, 0 is the minimum. So you could you could do a calculus problem using pre-cal. So what I tell my students all the time is that all of the techniques we learn in pre-cal, you take with you to calculus and you continue to use them. You use those transformations. So don't think that calculus is just going to be change your life. It will, but it's going to require you to know everything you learned before you got to that class. And so that's when you pull all of that knowledge together to solve problems. So I wanted to do this to kind of give you a way of seeing everything at work. Now, what we want to do is talk about division. Now, we're good at multiplying, polynomials. We can apply the laws of exponents. We square things, we square each factor. It makes our life really easy. We can add polynomials, collect terms, the distributive law, we're fine. But when it comes to dividing polynomials, we need to say a little bit more about that. So this is going to be the division algorithm. But this will showcase the factor theorem and the remainder theorem, which I've really already used. I already used the factor theorem. I had no choice, but now we're going to just state it and say, here's what we did. So in this case, we're going to say, oh, sorry. I've got extra sheets here, too many sheets. We're just going to call this, and we just did that, right? 3.3, division algorithm. It's like, oh, Professor Ron, we're going to do section 3.2 again with a different subject. Division algorithm. That is, just like we divide, you're thinking when we divide integers, the division algorithm for integers, is this the same thing pretty much? Absolutely. So we say divide polynomials by polynomials. So you're thinking, okay, you can thinking, well, I'll just divide any polynomial by X. I just put a fraction bar X and then X absorbs and I'm done. I'm a genius, kind of thing, and you're thinking, yeah, that's not too difficult. But when we change it up a little bit and the polynomial is a little bit more complicated, how do we deal with that? So let's state the actual theorem that we're going to use. So this is the division algorithm. And I'll use the notation that Dr. Stewart uses. Let P and D be polynomials. And we'll usually think real polynomials, but this would be certainly fine for complex polynomials. So we're always going to look at everything being part of the complex polynomials. Okay, so I don't want you to think that this doesn't apply there. Of course it does. Where the degree of D, now of course this is not required, but Dr. Stewart does this. We're just going to say that the degree of D is at least 1. It could, and I'll just say degree of D equals 0. The constant term is fine. It'd just be like dividing a polynomial by a number, like a 3. No big deal. It's still a polynomial, but we'll just focus here. But if you're thinking of it that way and you read it in another book and they don't make this restriction, then it doesn't weaken anything. Then there exist unique polynomials. This theory is a little bit more complicated, but it's doable, but it's really not. What I'm going to do is I'm going to show you the validity of it using numbers. And the best way to do it is using the construct of degree. But a lot of books would like to do it by contradiction, but I don't know if that usually help students very much. But that might be something you want to investigate as you go into higher mathematics. So we have unique polynomials Q and R such that is P of X, and we're using these letters to represent words. We'll think of D as divisor. Divide P by D. Q is going to be the quotient, and R is going to be the remainder. So Dr. Stewart uses letters that are useful to remembering this. So we're going to say P of X is the divisor D of X times the quotient plus the remainder. And in this case, where, again, the degree of R, remember, we can have a zero, a constant polynomial, which is degree zero. We'll talk about that. So the degree of the remainder is kind of like you keep dividing. It's like if you're dividing two numbers, you just keep going until the remainder is less than the divisor. And then I'm done. If you're dividing by 7 and then your remainder, you subtract and say, oh, I'm left with 3. Okay, remainder's 3, I'm done. The similar thing with polynomials is that you keep the division process until the degree of R is actually less than the degree of the divisor. So we say degree of D. So this gives us an algorithm that is certainly in line with the division algorithm for integers. It's the same thing, basically. And so one thing that you've already seen in college algebra is that another form of writing this looks like this. P of X, if you divide everything by D of X, then that just leaves the quotient plus R of X divided by D of X. So sometimes this form is useful, especially when you're doing rational functions and you have slant asymptotes. For instance, this turns out to be a linear function and this is the fraction, and you're thinking, oh, okay, or that'll be a constant and you get a horizontal asymptote. So the idea here is that sometimes this form is better. And of course, when you're doing your WebAssign, you need to type your answer based on the form that they request and don't make it up. Often, a lot of times when it comes to WebAssign, don't assume things about the problem that aren't there. And if you work the problem, make sure that you're following the formatting. If the problem already puts in parentheses for you, you don't have to put in additional parentheses. I mean, just make sure that you're following the instructions. And boy, I know that's hard to do, but it will make you better. You know, as a math professor, we follow our own instructions, and even sometimes that's difficult. So again, I'm asking you to do what I do every day, which is follow instructions. Okay, so what we want to do is to see why does this work? And then do the factor theorem and the remainder theorem. So for instance, here's an example of this. We're going to think of the number. I just made this up because as I've done proofs of this theorem for my honors sections, I used to come up with these neat little examples to motivate the proof, but we don't do the proof in this class. But again, you should investigate it as you move into higher level mathematics. So I'm going to think of 215 as 2 times x squared plus 1x plus 5. Well, of course, x is equal to 10. So I'm going to think of this as the base 10 rendering. So 215 is just 200 plus 10 plus 5. Well, I do that all the time when I'm doing arithmetic. But we can think of this as just a polynomial in x, where x is actually 10. I mean, if this is true, this should work. And it is true. And so it kind of gives you an idea that we just didn't make this up. Now, I'm going to pick another number, 25. And we're just going to write this as what? This will be 2 times x plus 5. Again, where x equals 10. Of course, 25 is just 20 plus 5. So the idea here is what we're trying to do is think of the numbers, these integers here, as polynomials. So another thing that we're kind of focusing on, and you've noticed when we do this class, we've been doing a lot of work with integer polynomials that look just like that. And so that's been the focus. Again, you can have any kind of coefficient you like, but the focus in this class will be on integer polynomials. We can change it up as much as you like, but then of course the theory starts to fall apart, and trying to find zeros is extremely difficult. So we're going to focus on the integer polynomials. So now you're thinking we're going to divide 215 by 25 using the division algorithm. So here's what we'll do. This will be the long division. And I'll show you some shortcuts, but right now this doesn't provide us with a shortcut. So we'll have 2x plus 5, and then we'll have 2x squared plus x plus 5. So now we're going to look at this as saying, okay, we're going to divide 2x squared, just start at the top like we're dividing two numbers. We're going to divide 2x squared by 2x. So over to the side here, let me just do a little sidebar up here because I'm going to use this space. We'll say 2x squared divided by 2x. Well, the 2's absorb and one of the x's absorb, and that just leaves us with x. So that we know how to do. So we're going to say 2x squared divided by 2x is x. And then we multiply and subtract and see what's left and see if we can keep going. So now we say x times 2x is 2x squared. Well, we already knew that because we did that computation. And then x times 5 is going to be what? 5x. So plus 5x. And now, just like with regular integers, we'll subtract. If this is a division algorithm, we need to see what's left over and to see if we just keep going. So now the 2x squared minus the 2x squared is 0, and then the x minus the 5x will give us a negative 4x. And then, of course, we can bring down the 5 if you like. Now, if we check, we go up here, we say, okay, well, the degree here is 1, the degree here is 1. It's not less. So the division algorithm says, keep going. Okay, so now we say, okay, now let's do another sidebar, very simple. So we say negative 4x divided by 2x. Well, the x is absorbed, and negative 4 divided by 2 is negative 2. And so we say minus 2. Now, of course, we know that negative 2 times 2x is negative 4x. We did that computation. So we're just writing down something we already know. And then we say negative 2 times 5, that'll be a negative 10. Now we subtract, just like we do in regular division. And so we have the negative 4x minus the negative 4x. Of course, that's 0 because the minus minus becomes plus. And then we have 5 minus the negative 10, which is 15. And now we look, okay, let's go up here to the theorem and say, okay, well, this has degree 0, that has degree 1. The theorem says stop. So we stop. Because that has degree 0, which is less than degree 1, as we have here. So again, when we get to this restriction, then we're done. And so now this implies, if you will, and we can write this with the x's and all that, then we'll put in the numbers, and then it's like, oh, wow, it does work. So we have 2x squared plus x plus 5, that's the p, equals the divisor 2x plus 5 times the quotient x minus 2, and then plus the remainder plus 15. So there's the division algorithm. And we see, as we thought, the 2x plus 5 does not divide this because the remainder is not 0. Well, we expected that. So now we're thinking, all right, does this work for us? Okay, well, let's just go ahead and look at this. Let's replace x with 10. So equivalently, x equals 10. So we have what? 215. X equals 10. Well, we know that's 25. Well, just stating the obvious. 10 minus 2, that's an 8, plus a 15. Absolutely. So, exactly. So if we divide 215 by 25, we get a quotient of 8 and the remainder is 15. Same thing as if we had treated them as polynomials. So this makes sense. This is called long division. So we call this long division. So when it comes to polynomials, we can divide them just like we divide integers, like you're in a number theory class. So the idea here is we can actually divide polynomials, and there's some instances when we can circumvent this procedure if the divisor is very simple, like an x minus c. That's going to be called synthetic division, and you've seen that in college algebra. But we don't get that luxury unless the divisor is very simple. Otherwise, we're kind of stuck with the long division. But we'll take it. We'll take it because the long division here just mimics dividing integers. We don't normally write things as polynomials. We just, kind of put all the coefficients together in base 10 and do the same thing. This just spreads things out for us and actually makes it easier. I don't know if a fifth grader would agree with us, but what we want to see here is that when it comes to the division of polynomials, we're mimicking the division of integers. So we're not really introducing anything new. The objects look a little bit different, but the theoretical construct is the same. Okay, so let's go ahead and write down the theorems that result from this. So now you know how to divide polynomials, and then I'll mention the synthetic. So again, this is kind of fun. This is where we start thinking about polynomials more abstractly, but it's still in the guise of doing arithmetic like we did in general math. So the first result is the remainder theorem. These are easy. The remainder theorem is really simple. And this is where we get to think about synthetic division. So I'll say let P of X, these will be fun. You'll enjoy using these. You probably did this in college algebra. Let P of X be a polynomial. And the C that I just mentioned, I'll just say the C could be any complex number. Usually it'll just be a real number, and this will be fixed. So say we fix a complex number like 2 or 1 or something, okay? But this is also valid for imaginary. If P of X is divided, this is where the x minus c comes in, divided by the polynomial x minus c. That's what I was saying before. X minus c, well, tell me about that. That's a polynomial of degree 1, and it's also what? Monic. The leading coefficient is 1. I've already talked about that when you complete the square. You should know how to complete the square. Like I say, the quadratic functions were complicated, but once you see how it works with what we're doing now, it's like, not so bad. not so bad because things are starting to fit together, come together. That's one nice thing about math. It's like doing the foreign language. The more Spanish or French or German or whatever you're taking, more you take, the more you understood the first class. And then you think, how did I ever get through the first class knowing so little? When you really think about that, you know, when we ask students to do math, that's why I'm so foundational with my teaching. I mean, I'm asking you to do a lot, but I'm not just going to ask you to memorize everything. I'm going to show you why it works and give you techniques to convince yourself that it's actually valid. So again, just think about your foreign language class where you learn new grammar constructions, you learn new vocabulary, and you just grow, grow, and grow. Math is the same way. Now, this might be a surprise to you. Then the remainder is P of C. And you're thinking, well, that's just a simple use of the division algorithm. Because you told me what you're doing. Professor Ron, you said divide P of X by X minus C. And that's degree 1. So the remainder will have to be degree 0, which is a number. So that's the number right there. You evaluate P at the fixed number C. And you're thinking, oh, okay. If P of C is 0, then C is a 0. You're like, oh, okay. So, now see, that's how the synthetic division is going to work. But let's just see that this is true, and then we can do the factor theorem. So I want you to see how all of this is coming together. And it's like, oh, I think we've been doing this all along. It just maybe never called it the remainder theorem. So why is this true? Well, we can just use the division algorithm. Use division algorithm. Use division algorithm. So now we'll say there exist unique polynomials Q and R such that we just fill it in. P of X equals the divisor. Okay, the divisor is X minus C times the quotient. So you see how we kind of needed this back in the last section, but we intuited the ideas based on what you'd already done. So we get the divisor times the quotient plus the remainder. And obviously we know this, the degree of R must be 0. We know that. This degree is 1. So when we do the division algorithm, the only thing left for R is 0. So R is a number. R is a number. It's a constant polynomial. So we get that for free. And so we're thinking, oh, now I get it, because we can just evaluate polynomials all day long. Then I told you this was easy. As long as we have the division algorithm, Dr. Sarah Witherspoon, who is now the department head of the mathematics department at Texas A&M in College Station, where I attended grad school, I took her for graduate algebra. Boy, she made it look easy. But she'd say, we have a big hammer. This is a big hammer. And I said, oh, what do you mean? She says, this will help us solve many problems. So we look at the division algorithm as being a big hammer, because it's like, okay, it illuminates all these other ideas. But the problem is the big hammers take the most effort to prove. But once you get that proof, you have this nice result. It's kind of like the fundamental theorem of calculus is a big hammer because it helps you solve so many problems. That's why they call it the fundamental theorem of calculus. So now we'll say, as Dr. Witherspoon says, with the big hammer, we can now evaluate P at C. So we say P of C will be now C minus C times Q of C. So we just replace X with C plus R. R is just a constant, so it's just R. I mean, you could say R of C, but it's not going to change it. But now, of course, this will be 0 times the number. So this is 0 times Q of C plus R. But of course, 0 plus R is just R. And so we're done. So the remainder is P of C. So that's like, okay, so now if we had a way to test division, for instance, we're thinking if we divide by X minus C, is there a quick way to do that so we can check for zeros? Okay, so if you had a nice theorem that says, okay, here's a list of numbers that might be zeros. And then you say, okay, I want to use the remainder theorem, but I'm going to do the division process using a modified technique that doesn't require the long division that goes on forever. So this will play a big role in what we do when we check for the existence of zeros. So there's more to come here, more to come. This is really important right here. And again, if you recall this from your college algebra, you know this is an important technique. And now the next result, which we've already used, which is kind of like the zero product law, is the factor theorem. So if we look at this, we're going to say the same thing we did before. Let P of X be a polynomial. Let P of X be a polynomial, and we're going to assume we have a zero. We're going to say P of C, well, let me make this, let me go parenthesis, less looking like a C. P of C equals 0 for fixed C, some complex number. Maybe it's just a 2 or 1, you know. So we have a 0. Then we're going to look at this and say, okay, so we've got a 0. What does that mean? Well, let's see here. Then, and I've used this before, we can say P of X equals X minus C times Q of X if and only if P of C equals 0. So it looks like you kind of said the same thing again in the conclusion, but we added to it. So we've got a 0 of a polynomial. And we use this with the local behavior. I mean, we didn't, that we couldn't get around it. But here's the idea. If you have a 0, then you must have the corresponding factor X minus C in P, because that will be the only algebraic structure that will annihilate P. So when you think about the structure of a polynomial, you have a 0, C, say it's 2. That means you've got to have an X minus 2 buried somewhere in that polynomial with this type of factorization to annihilate it. So the idea is that when we said we had a 0 and I said X minus C to some power M for the multiplicity, and then I multiplied it by the Q of X, that's exactly what I was doing before. I was using this construct with the division algorithm, even though at the time I had not stated it. But again, Dr. Stewart decided to throw this in before the division algorithm, which is fine. It's fine. I mean, that you have that license as a mathematician. But the idea is that it seemed obvious, and now it should be very obvious. So when you look at this, you're thinking, well, why is this true? Well, this is just basically that result. Why? So we're going to say again, by division algorithm, well, let's just say this. let me write this first. Let's make this assumption. We'll do it in just one swoop. We'll do this. Suppose in this particular case, that we look at this, suppose we have the above hypotheses. Let me state it this way, so it clues you into things. By the division algorithm, there exist, same thing, polynomials Q and R, just like what we did up here, Q and R, such that, and they're actually unique. And when I did here, let me go ahead and say such that P of X equals X minus C times Q of X. Now, plus R, where the degree of R equals 0. Same thing we had up there. So we're assuming we've got this. So the division algorithm gives us this, which is the same thing I wrote up here, exactly the same. Then, now we go to here. P of C equals 0 if and only if P of C equals 0, then we've got this result here, division by X minus C, then we know R is 0 right here from the remainder theorem, if and only if R equals 0. And this is just remainder theorem. I didn't want you to think I wasn't assuming this part here. I mean, I'm assuming this, so I go from here to here. So I wanted to make it clear that I was keeping this in mind. Then the division algorithm. Then if R is equal to 0, what does that mean? What does that mean? Well, then X minus C is a factor. Then we just take this part and say P of X equals X minus C times Q of X. They're equivalent. So we use, I'll say it again, this is the big hammer. As Dr. Witherspoon says, the big hammer. She attended the University of Chicago for graduate school, and she lamented at the time how difficult it was. But she's brilliant, and it was a pleasure to go to some of her seminars and to listen to her lectures. I was always running from a Calculus 2 lab I was teaching, running to Zachary to get to her class. And she always laughed when I came in because I was always like a minute late. And I said, I'm so sorry. I can't seem to shut up quickly enough in my recitation to get over here. And she would always giggle at me. But the thing is that the phrase big hammer stuck because this is the key. It was the key here. And now if we've got the big hammer, then we can say, okay, if C is actually a 0, then we say, all right, great. P of C is 0. Well, boom, right here. That's the remainder. So R is 0. Well, then boom, right here, that's 0. So indeed, X minus C is a factor. So the proof is easy. I mean, the ideas are simple as long as you have the so-called big hammer, which is the division algorithm. Okay, that is, we can divide a polynomial by a polynomial. So I don't want you to think that this is difficult because it isn't. The actual execution of the proof of the division algorithm is a little bit more subtle, that takes a little bit more maturity to go through. But when you use the division algorithm, you can see how these are very simple results. So major results give rise to other results that turn out to be extremely useful to us. So I wanted you to see that when it comes to this, it's very, very simple. Now, let's build a polynomial. And then we'll say a little bit about the synthetic process. I'll show you how it works. So First, we want to build a polynomial, and we're going to use the factor theorem. So, so we want a we want the degree of our polynomial to be 4. We want integer coefficients, so no square roots, no imaginary numbers. We want integer coefficients like we always do. I keep saying, you know, this is pretty much what we study in this class. We want zeros to be, let's see, in this problem, we've got a 1, a -1, and a square root of 5. And we want the constant term, of course, which would be p of 0. That's like the y-intercept. We've done that before. We want that to be 15. Now you're thinking, with all of this and executing a restriction on the constant term, this is unique. In some instances, the problem might be, okay, build a polynomial with these zeros. Okay, then the polynomial is not necessarily unique. You can multiply it by anything. The idea is that if you start specifying points, then that will move the uniqueness. That will put you into a unique polynomial. So just be aware that in WebAssign, they might say, well, give me a monic polynomial that has these zeros with integer coefficients or whatever. So you're not necessarily doing unique, but in this case, we'll just say P of X is unique. And this is going to basically follow from complete factorization when we talk about soon the fundamental theorem of algebra and its corollaries, just like we've got the division algorithm and the corollaries, the what factor theorem and the remainder theorem. So what we can do is use the factor theorem very simply. So we've got zeros and then we have factors. This is easy. It's not hard, not nearly as hard as some of the word problems that you all struggle with, mixture and time, rate, distance. I mean, it's amazing. It's amazing that if you think about what we do and do everything logically, nothing should be hard, but we just have to follow the recipes that get us where we want to go. So now if we have 1 and -1, well, a direct application of the factor theorem says that we need what? We need 1 minus, excuse me, x minus 1, because we want c to be 1. And here we need x minus -1. So this is x minus c, but of course that would just be x plus 1 if you wanted to write it that way, which would be okay. So if we have a 0 of -1, we must have that factor to annihilate the polynomial. If we have a 0 of 1, we must have this factor to annihilate. Now, the square root of 5, we can remedy with a quadratic factor. We can't say that the 0 is this and stay within the constraints of the degree 4 and the integer coefficients. So you're thinking, you know, maybe we could just do 2 of them and multiply them together, or just say we can get plus square root of 5 and the minus square root of 5 together. So we're going to say we'll get these 2 zeros here if we have this factor, x squared minus 5. So now what we're going to do is think of a difference of 2 squares. But see, again, the cubic polynomial would be somewhat difficult to do unless we varied some things here. So what the problem is saying is that bump up to degree 4, get this 0 using the quadratic term here, this factor, which will again give you an additional 0. We're not saying that you can't have other zeros. We just have to have degree 4, and we have to have those zeros and that constant term there. So now this implies, if we have the factor theorem, we can take the product of all of these. So this will be x minus 1, x plus 1, and then x squared minus 5. But now, of course, this is just a difference of two squares like that is. So let's just ride the wave, x squared minus 1 times x squared minus 5. It just really depends on how many terms we have as to how much work it's going to be. So now what does this equal? We'll just use the distributive law. X squared times x squared is x to the 4th. X squared times negative 5, this will be minus 5x squared. And then we have negative 1 times x squared, so minus x squared. And then negative 1 times negative 5 plus 5. So if we just combine like terms, we get x to the 4th minus 6x squared plus 5. So we see this is really quadratic form. It's quadratic in x squared, which is not a surprise based on what we've done here. Now you can think of this in terms of the complete linearization, where we think of this polynomial times some number a, or we can just say, okay, we can take any multiple of this polynomial to define p. So if we need this to be the 15, then we can simply multiply this polynomial by 3, and the 3 will give us the 15 that we need. So we define p of x to be 3 times x to the 4th minus 6x squared plus 5. Again, you can do this by complete factorization, the linearization, or you can do it this way, trial and error. And so that'll just give us 3x to the 4th minus 18x squared, and then plus the 15. Now, of course, now that is a unique polynomial, because again, it has these specific zeros and it has this specific term here. This is unique, and this is unique. The idea is when you start specifying points on a graph other than the zeros, then that is a higher level of specificity. Zeros, we just take the factor theorem, need that factor, need this factor, need this factor, done. Get a nice monic polynomial. But then, of course, when you start specifying particular values other than the zeros, then that's where you introduce the uniqueness. Now, one thing that's interesting about what we just did is that you're thinking, okay, this might be a problem that I would do in a physics class or an engineering class. Maybe I was doing a model or something, and I came up with a particular polynomial function that's going to serve me in solving another problem. And so you might, be modeling a particular schematic using mathematics. And so, we think about this and say, okay, well, this is probably something that I would like to be able to do. This is called building from the ground up. Normally, though, in a math class, we think of starting with the product and then unraveling it. So if you're in on the ground floor, you understand it. But if someone just serves up the polynomial and they say, okay, break it down, unravel it, that requires a little bit different technique. And this is where we can use the remainder theorem and the division algorithm to really make this process easy. So for instance, in all of these cases, let's just look at this. This is called synthetic division. And the idea is that we circumvent the long process because of the fact that we have a monic polynomial of degree 1, where we have a lot of extra baggage that we don't need to consider. And so what we can do is we can make a little table. Sometimes it's called a tableau if you think in French. And you simply write the coefficients of the polynomial in descending order. and place zeros for the values or powers of x that aren't there. So we have a 3, we have a 0, we have a negative 18, then we have a 0, then we have a 15. So what we want to do is represent the coefficients of all the powers of x, starting with the leading term. Okay, so the leading term has coefficient 3, the cubic term has coefficient 0, the squared term has coefficient negative 18, the first degree term has coefficient 0, and the constant term is 15. So for this process to work, it's kind of like we were doing the long division process. We always want to put in placeholders where we have certain powers that don't exist. I mean, it's a 0, the 0 coefficient, so it exists, but we just don't write it normally. So these are placeholders. And so now what we would do is we would say, let's divide this polynomial by x minus 1. Okay, so what we do, if we divide by x minus 1, what we do is we take the number that's basically what? To the right of the minus sign. We always want to preserve the minus sign. And so you're thinking, oh, we're done. The coefficients add to 0, so we're done. But I just want to show you. You put in your 1. So we can divide by x minus 1 and use the remainder theorem without having to write down the long division process. So how do we do it? And this is just a modification of long division. You bring down the leading coefficient, then you multiply the terms. And because we're choosing the 1 to the right of the negative, we multiply these two numbers to get 3. Then we add to the 0, the next coefficient. So 3 times 1 is 3, plus 0 is 3. That's the technique. Then we keep going. Now we do it again. 3 times 1 plus the next coefficient, negative 15. And then we do it again. Negative 15 times 1, which is negative 15 plus 0, negative 15. But you already knew this. Negative 15 times 1 is negative 15 plus the next coefficient, 0. So that's the remainder. Division by x minus c has remainder p of c. So p of 1 is 0, but we already knew that. But say if you were given this problem on a platter and you had to deconstruct it, then you would want to try to figure out, okay, does this have any rational zeros? So the idea here is that we can use this synthetic division process to use the remainder theorem in a much more efficient way. The key is that in this case, and let me write this, this is in more general terms, division by x minus c. And we always preserve the minus. So if it's a plus, we have minus minus. And this is the c right here. Bring down the coefficient, move forward. Now, one thing that's interesting about this, and we can think about this, is that based on this, it doesn't matter what the c is. So let's finish up. We have x minus the square root of 5. So let's put in the square root of 5. So bring down the 3. 3 times the square root of 5 plus 1, plus 0, that's 3 times square root of 5. Okay, and now we do it again. So we multiply. So we have 3 root 5 times root 5. Okay, so that's going to be root 5 times root 5, which is 5, times 3, that's a 15. 15 plus a negative 18, that's a negative 3. Keep going. Negative 3 times root 5. Well, that's negative 3 times root 5 plus 0, negative 3 root 5. And now lastly, we say negative 3 root 5 times root 5. Well, that's just going to be a 5 times a negative 3, which is negative 15 plus 15, 0. So the idea, it doesn't really matter what number we put here. Usually when we do this process, the numbers will be integers or fractions because we'll be looking for rational zeros. But there's certainly, we can't discriminate. The C is C. So we know that we should get 0 here because we just built this, and we know that square root of 5 is actually a 0 because we made it that way. So with the synthetic process, we actually execute the division algorithm without having to do the long process of long division. So again, bring the leading coefficient down, multiply, add. And you add, you don't put an extra row here. That, I don't know why you ever get taught that. Don't do that. And we're going to figure out what it means by the signs of these entries here as to how we should negotiate utilizing certain theorems. For instance, to say, do we need to keep going larger or do we need to get smaller? Are we wasting our time? Are we not wasting our time? So we're not gonna have the addition row in the table. You're just gonna do that to the side and then only put the entries here that make sense. I mean, otherwise this process is useless. And I'm not really sure why it's taught that way. It makes absolutely no sense. I'm just thinking, fill up the table with the ideas that make sense. And then this gives you plenty of information. And we'll talk about what kind of information this actually gives us. Because when you look at this row, it's not very robust, but eventually you may get to a point where you're going to say, well, looking at these coefficients, I don't need to try any larger numbers because I'm just going to end up with the more positive numbers. We have to be able to use some arithmetic restrictions that say, okay, if you're looking for a 0, don't go in that direction, go in this direction because there might be one here. But there's never a guarantee on anything. Polynomials are very quirky. So, like I say, we have to respect the mathematics. So just remember on Thursday, you have a free day. I mean, it's sleep in, study if you want. You don't have any formal classes. So I'm going to go ahead and do some review problems on Thursday. You are certainly welcome to come to the lecture. I'm just going to use that as a time to record it. And if you're hanging out, fine, no big deal. I will work through some problems. And then of course I'll post it to Blackboard, the link, just like this lecture will be posted. So you can utilize that if you like. This is just an opportunity to do some review problems to help you focus for the test. But again, as you work through your WebAssign and you do your quizzes and you look at the practice test on Blackboard, of which there are very many, you'll see lots of nice examples that will help to kind of pull everything together. And so on Thursday, if you want to come to class and do some review problems with me, I'll work through them like a regular lecture. You are more than welcome. If you want to sleep in, get some extra sleep and take it easy and then do some studying later that day, then certainly that's also on the table. I just want to let you know that we're having the College Community Day, so there are no formal classes, but for my Monday, Wednesday classes, I'm going to do review. And so I don't want to leave it out for you all, but I don't want you to think that I'm requiring you to be here. This is kind of an optional class. And so use it as you find beneficial to your situation. Okay. Well, I enjoy doing what I do. I will say this. I enjoy teaching the calculus sequence. I actually enjoy teaching linear algebra, but my linear algebra class didn't make. I mean, those classes are really challenging. But I want you to appreciate math for its inherent elegance. That is, it always pushes us in the right direction. It's like, okay, do this, or oh, wait a minute, you need to check this because this is not consistent. So as you study, always make sure that your work supports what you intend. And I think you're going to find it to be very rewarding. So enjoy the warm weather while it lasts. I think we're going to get some Arctic weather, at least for us. We'll see how it goes. And I guess with my Dr. Phil head, I'll need to make sure I've got a nice cap on so I don't freeze to death. But I'll see you later today. If you come to the sessions, I'll do conference hours, one around noon, and then of course one in the later afternoon. And so if you take advantage of those, fine. I'll see you. Otherwise, I'll possibly see you on Thursday. So everybody, good luck as you study and prepare, and get some rest, and take care of yourself. We'll talk to you later. Thanks, everybody. Oh, and yes, you all have a good day too. It's not just for me. It's for everybody. And just take care of yourself. You know, take your vitamins, and be safe as you go outside. Okay. Bless you all.